Good morning, everyone. My name is Shirish Chandrakar and I'm a research scholar at IIT Kanpur. My thesis is focused on comprehensive experimental and computational investigation on hydrogen-induced deformation micromechanism in titanium, net zero emission, and targets set by different nations with a deadline of 2035 to 2070. However, heavy industries and related sectors such as fuel, chemical, power, transport, and aviation are heavily dependent on fossil fuels and which are the major contributor to carbon dioxide. Hence, it is very important for us to decarbonize this sector, and this is where the hydrogen infrastructure play an important role by providing an alternative clean energy solution. However, there has lot of safety concern regarding the hydrogen infrastructure, which has caused various accidents over the year, and this is due to the lack in fundamental understanding of hydrogen embrittlement. Hence, it is very important for us to understand hydrogen embrittlement to build a foundational element to build a hydrogen economy. So for this we did in situ tensile test, in which we do the tensile testing inside the scanning electron microscope, from which we found that there is a reduction in ductility, and this was due to the localized deformation that is occurring in the basal oriented grain, that is the red color grain, which is responsible for the reduction in ductility. Hence, we planned our next chapter, that is the effect of crystallographic texture on this deformation micromechanism. What will happen if we remove all this red color grain? Will the hydrogen embrittlement resistance increases or decreases? So on testing the second orientation, we found that in this second orientation the hydrogen embrittlement resistance increases as the uniform ductility reduces by 28% rather than the 40% in the previous case. And all this hypothesis was supported by a crystal plasticity simulations. To further understand the service condition and hydrogen susceptibility, we did cryogenic tensile testing, in which the commercially pure titanium generally show a very good strength and also the ductility. However, in the presence of hydrogen, there is a drastic reduction in the ductility, and this is due to the deformation shift from the combination of twin plus slip deformation to only twin deformation that is happening at cryogenic temperature. So the novel outcome of this thesis is that we developed an understanding on the deformation micromechanism of titanium in hydrogen environment, and the second is development of computational models so that we can predict for different microstructure and loading condition. And then we developed a hydrogen embrittlement resistance metal using a crystallographic in texture engineering. And lastly, to understand the behavior at extreme condition, we also perform cryogenic testing, which is important for the development of safety in hydrogen infrastructure.